suppose we have ay double prime plus by prime plus cy equals 2. Y equals to some function. Okay. In that case, we call this non-homogeneous. If you have a non-zero function here, then suddenly this problem becomes harder. So let me give you an example, and probably after this you'll see what our plan is. Okay, so to tackle this, we're going to do y double prime. Let's see. Let's make it simple. Y double prime plus y equals to just 1. That looks really simple, right? We're just looking for a differential equation, y double prime y plus y equals 1. I can't think of a simple non-homogeneous second order differential equation. Now, as I explained, we're just guessing, right? Can you kind of try to guess the solution of this differential equation?
E to the x.
E to the x double prime is e to the x. E to the x plus e to the x will be 2 times e to the x, and that won't agree with 1, so it's not going to work. Hint, it's simpler than that.
0, 1.
1. Y equal to 1 is the solution. A constant function. Because if y is 1, what's y prime? 0. What's y double prime?
0.
So this is 0, that's 1. 0 plus 1 is 1, so it works. Right. Okay, good? So y equals to 1 is the solution. Now, one thing you might want to check is whether y equals to some constant times 1 would be a solution. Does this work? What happens if you try to plug that into the left side? What do you get if you plug this to the left side? What do you get?
0.
This will be 0. This will be c. So 0 plus c will be c. And unless c is 1, it's not equal to 1, right? So what you've just witnessed is the fact that when it's non-homogeneous, no longer you can play this game of taking a solution and multiplying by a constant. We had some fun with the homogeneous case because whenever you found one solution, you automatically found at least 1/2 of the solution because you just times it by the c, right? But that no longer works here. But instead of that, here's something else for you to think about. There's something called the complementary differential equation, which is the homogeneous case. What's the solution of this equation?
0.
0 is one solution, but in general, can you find the general solution? Maybe this is more familiar to you. What kind of function has second derivative equal to negative of itself?
Like a sine or cosine.
Sine and cosine. I mean, you could write down the characteristic equation, which is r squared plus 1 equals to 0, and find r equals to -1 equals r equals to, meaning that r is plus or minus I, which is 0 plus minus I, and in that case it's 0x c1 times cosine of 1x plus c2 sine of 1x, right? Using the standard form, if it's alpha plus minus beta I, alpha goes here and beta goes there, right? But alpha is 0. What's e to the 0? 1. So that doesn't need to be there, because that's just times 1. And that's exactly what you've predicted, right? cosine and sine are the two functions whose derivative is same as negative of itself. So we got this from the standard solution, but you could also just see this and say, hey, the solutions are cosine x and sine x. That's also possible. Either way, this is the complementary solution. Okay? And what does that have anything to do with this, you might ask? And this is how they're related. All you have to do is now take that complementary solution and add to it this one particular solution you found and call that as y. Now it consists of two parts. Okay. So this part, which we call y complementary, because it's the solution to the complementary equation, and this part we call y particular, because it was just one particular solution we found out just by trial and error. Okay. And I claim that if you plug this into the left side, you get the right side. Why would that be? Okay, so let's try to convince ourselves by actually plugging it into the left side. Okay. So if I take the second derivative, what do you get? Negative C1 cosine x, right? And then two derivatives. Take sine and differentiate twice. What do you get?
Negative sine.
Differentiate this twice. What do you get?
Zero.
Okay, so then y double prime plus y gives you this plus that. What do you get?
0 plus 1.
Most of them will cancel out, right? So you see that the complementary solutions will go away, it will become 0, and at the end of the day, what survives is your particular solution, which creates the right side, which is this one. Okay? So we just found out that y double prime plus y is equal to 1 for any C1 and C2. Do you agree? We just calculated, right? So if I take this to be my y and plug it into the left side, I see that everything cancels out except this thing, which is equal to the one on the right, meaning that it satisfies this differential equation. Okay. Now, first question is, why do these things with C1 and C2 disappear? What's the reason? What do you think? YC is a solution to what? This equation, right? So YC, when you plug into the left side, what are you going to get?
0.
0, because 0 is on the right side, right? Okay. So that's the magic here. Whenever you take YC, complementary plus YP, as your y and you plug into the left side, the complementary ones will disappear, and you're going to see that the YP that you found survives, creating the right side. So that's good. Okay. That's the first question. That's the first question to ask. Why does this happen? Okay. Would it happen all the time? And the answer is yes. Whenever you take YC plus YP, YC will disappear, creating this solution to satisfy the differential equation. Okay. Second question is, if this is going to disappear anyways, why do you want it? What do you think? Why would we want it?
Looking for all the values.
Because you're looking for all possible solutions. Okay? Because you're looking for all the solutions of this, and I'm claiming that this is the all possible solutions. Right? Now let's think further why that's so. How many free parameters does the right side have? Count it. How many do you see? I guess you don't know the word free parameter. C1 is a parameter which you can set to anything, right? C2 is another free parameter. You can set it to anything. Whether you take C1 to be 3 and C2 to be 5 or anything else, it will always satisfy the equation on the left, right? So how many free parameters do you have? 2. 2 free parameters, okay? The order of this is second order, right? So how many free parameters do you need to have? 2. We have it. So that's it. It means that what we have in front of us is the most generic solution of this differential equation. Now, let's see what that really means. It means the following. If I have this equation with, say, y of 0 is 3 and y prime of 0 equals to -5. I just put some random numbers here, okay? Now, does y equal to 1 satisfy these initial conditions? No, it doesn't. As you can see, it's a constant function, so y of 0 is 1 and y prime of 0 is 0. Only when that's the given initial condition, this will be a solution to this differential equation. Right? But if you want the solution of this differential equation with this initial condition, the mathematical theorem of uniqueness and existence tells us that, oh, there's definitely one solution, and it's a unique one. There's only one solution that will satisfy this differential equation with these 2 free parameters for initial conditions. Okay, and you can find that solution by using this one instead. Right? If you plug in 0, you know that C1 plus 1 should be 3, so C1 must be 2. Okay, so this should be 2. And if you differentiate this, you get C2 cosine x, so C2 should be -5. So if you have 2 cosine x minus 5 sine x plus 1, that will be a solution of this differential equation satisfying these 2 initial conditions. So whatever initial conditions you throw in addition to this, you'll always be able to find this type of solution with some C1 and C2. That's why we're sure, 100% sure, with the help of the theorems that mathematicians prove, that what we have in front of us is the most generic solution of the differential equation. Okay, does that make sense? All right. So let's try to come back to our original form and write down the plan. What's the plan? Our plan is to, step 1, find one particular solution. And we are going to call it YP, P for particular. Right? Step 2, find the complementary solution. I.e., that is, it's a solution of YC, a solution of AY prime plus B, AY double prime plus BY prime plus CY equal to 0. And then step 3, which is the final answer. Step 3, Y is equal to YC plus YP. That's the general solution. That's how you tackle a homogeneous differential equation. And as you can see, it's definitely more complicated than solving a homogeneous one, because when you're trying to solve a non-homogeneous one, you have to solve the homogeneous one before getting to the non-homogeneous one. Okay? So it's definitely harder than just a homogeneous one. Okay? All right, so let me give you a second example. easy. Let's say you have y double prime plus 2y prime minus 3y equal to 0, equals to e to the negative x. How should we solve this? Now this time, just trying to guess the solution is not so easy, right? Do you have any ideas? What would you try if this was what you wanted to find? What would you plug into y to get that? Either negative x is what you would plug in, right? So if I take y as e to the negative x, y prime will be negative e to the negative x, and y double prime will be again e to the negative x. So y double prime plus 2y prime minus 3y will be e to the negative x plus, actually minus 2e to the negative x minus 3e to the negative x, which creates negative 4e to the negative x. Okay, so we didn't quite get e to the negative x, so what do you think? What should we do? This is not equal to the right side. Can we do better?
Negative e to the negative x, that's y.
If you put a minus in front, the final answer will be positive 4e to the negative x. So you'll still be, it will still be off by 4. What do you think? Yeah, that's what you want. So if you do that, then you're going to get over negative 4 over negative 4 over negative 4. That's going to be the solution. Okay? And then what about this? R squared plus 2r minus 3 equal to 0. That's the homogeneous, that's the characteristic equation for the homogeneous equation, right? Which is r minus 3, no, r plus 3, r minus 1. So you get r equals to negative 3 and 1. Therefore, what's yc? Y complementary. So if the right side was 0, you would write this as the characteristic equation. When you solve it, you get r equals to negative 3 and 1. So what's your yc? Y complementary. Two distinct real roots. What do you say? C1? I guess you guys are busy copying. E to the negative 3x plus C2 e to the x. Therefore, what's the final answer? Y is C1 e to the negative 3x plus C2 e to the x, and then
Minus
1/4
e to the negative.
e to the negative x. How many free parameters does this have? 2. Okay. Since these are linearly independent, then for different values of C1 and C2, you will always get different solutions, definitely. Right? So that's good. That's the generic solution of the given equation. Now, in the next class, what I'll do is I'm going to take this method that we just used, I'm going to improve it. Okay? And here's the basic idea. Here's the basic idea. We did this, we found this particular solution by trial and error, right? But sometimes trial and error are tricky. Can you make this more streamlined fashion? Can you make this streamlined so that it's easier to use? Okay? And here's the idea. Rather than doing trial and error, just look at the right side and say, well, you know, e to the negative x, if you differentiate, it always stays like this, right? So why not take our yp as some constant times e to the negative x, right? So you can make a guess. Then when you plug in the left side, you'll end up with negative 4a e to the negative x, and on the right side you have e to the negative x, and then you can say a must be negative 1/4. Plugging that back in, we get this solution. Okay? So that's a more streamlined approach, and such a method is called method of undetermined coefficients. Okay? So that's what we'll do next time.